Ice floats, and that one small fact is the reason life on Earth survived at all. Drop an ice cube into a glass of water, and it does something so ordinary you have probably never once stopped to question it. It floats. It bobs there at the surface, half in the water and half in the air, and stays that way until it melts. You have seen it 1,000 times, and it seems like the most natural thing in the world. But in the world of physics, this simple little act is deeply, almost unreasonably strange. Because ice is nothing more than frozen water, the very same substance, only colder and turned solid. And nearly every other material on Earth does the exact opposite of what that floating ice cube is doing. To see why, we need to talk about a single idea: density, how tightly a material's matter is packed into the space it fills. When something is dense, its particles are crowded close together, making it heavy for its size. When it is less dense, they are spread further apart. Drop a stone into a pond, and it sinks, because the stone is denser than the water around it. Rest a cork on that same pond, and it stays on top, because the cork is lighter, less dense than the water beneath it. Now here is the rule that holds true for almost everything else in the universe. When a substance cools and freezes into a solid, its particles slow down, draw closer together, and pack more tightly than they did as a liquid. That makes the solid form denser than the liquid it came from, so the solid sinks in its own melt. Melt a bar of iron, drop a chunk of solid iron in, and it sinks. The same is true for rock, for wax, for almost every material we know. By every ordinary expectation, a cube of frozen water should drop straight to the bottom of your glass like a tiny stone. And yet it does not. It floats. So what makes water break a rule that the rest of the universe obeys? The answer is hidden in the shape of a single water molecule, one of the most important shapes in all of nature. A water molecule is built from just 3 atoms, one of oxygen with 2 of hydrogen joined to it. But they do not sit in a straight line. The 2 hydrogen atoms cling to one side, giving the molecule a distinct bent, boomerang-like shape. That lopsided shape leaves the molecule slightly charged, a little negative near the oxygen, and a little positive out at the hydrogens. And opposite charges attract, so the positive edge of one water molecule reaches out and gently grips the negative edge of another. These delicate links are called hydrogen bonds, and they are the secret behind almost everything water does. In liquid water, these bonds are constantly forming and breaking, letting the molecules tumble and slide past one another, packed in loosely, but close. As long as the water stays warm, the molecules have enough energy to keep jostling, staying crowded messily together. But watch what happens as that water slowly begins to cool. At first, water behaves like almost any other liquid. As it cools, its molecules slow down, huddle closer, and the water grows steadily denser. This is why the coldest water in a lake tends to sink, sliding down to gather at the very bottom. But water does not keep getting denser all the way down to freezing. It stops short just a few degrees above it. Water reaches its greatest density at around 4 degrees Celsius, a little above the point where it turns to ice. Cool it past that curious 4 degrees, and something almost magical begins to happen. The water starts to expand again. The molecules, still slowing, no longer have the energy to stay crowded. Instead, their hydrogen bonds begin locking them into a fixed, orderly arrangement. And that arrangement, it turns out, actually holds them further apart than when they were tumbling freely as a liquid. When water finally freezes, those hydrogen bonds snap every molecule into a vast, repeating pattern, a crystal. But it is a remarkably open, spacious crystal. Each molecule is held at arm's length from its neighbors, locked into a rigid six-sided lattice. Picture the molecules in liquid water as a crowd of people packed shoulder to shoulder, shifting and shuffling to fill every gap. Now freeze them, and they suddenly join hands and step back into a wide, airy ring, a beautiful open framework full of empty space. That empty space is the whole secret. The same molecules now take up more room than they ever did as a liquid. And more room for the same amount of matter means one simple thing: ice is less dense than the water it came from. This is why water swells as it freezes, growing by nearly 1/10 of its volume, pushing outward with astonishing force. And it is why, against all expectation, ice floats, because it is nothing more than water holding itself open, cradling emptiness inside its crystal. That very same open, six-sided pattern is why every snowflake grows with 6 delicate arms, the shape of the crystal, written large enough to see. This might all sound like a small curiosity, a neat trick of chemistry. But it is far more than that. It may be one of the reasons you are alive. Imagine, for a moment, a world where water behaved like everything else, where ice was heavier and sank. When winter came to a lake, ice would form at the surface, then immediately sink to the bottom. Fresh water at the top would freeze and sink in turn, layer after layer, until the entire lake froze solid from the bottom up. Every fish, every plant, every living thing in that water would be locked away in solid ice, with nowhere left to escape. But that is not what happens, because ice floats. And that one fact changes everything. In the real world, the ice forms a thin skin across the top of the lake and simply stays there. That floating layer acts like a blanket, sealing in the warmth of the water below and shielding it from the freezing air above. Beneath the ice, the water stays liquid, hovering near that dense 4 degrees, and life quietly goes on through the whole long winter. Fish drift slowly in the dark. Plants wait in the cold. The living heart of the lake keeps beating beneath a frozen roof. Now widen that picture from a single pond to the entire planet. Our world has passed through long ages of deep and bitter cold, when ice spread far across its face. If ice sank, those frozen ages might have been almost impossible to escape. Oceans would have frozen from the bottom upward, turning to solid ice that even the summer sun could never hope to reach and melt. Life, which very likely began and sheltered in water, might have been crushed out before it ever had the chance to spread. Instead, floating ice sits on the surface, reflecting sunlight while always keeping a living ocean flowing beneath it. That one quiet property of water, the simple fact that its solid floats, may be part of why our planet stayed alive through its harshest chapter. And the story does not end at lakes and oceans. That same expanding force reshapes the world around us, one frozen crack at a time. Water seeps into the tiniest cracks in stone. When it freezes and expands, it pushes outward with enough power to split solid rock apart. Over countless winters, this slow and patient force helps grind mountains into gravel and carve whole landscapes into being. It is the same force that bursts a forgotten pipe on a freezing night, cracking metal and stone as though they were nothing. Even the humble pothole in the road owes its birth to water slipping into a crack, freezing and prying it slowly wider. So the next time you drop an ice cube into a glass and watch it bob quietly to the surface, take a moment to look at it again. You are watching one of the strangest and most generous quirks in all of nature, a substance that breaks the rules. and in breaking them, protects nearly everything that lives in water. A whole world kept alive by nothing more than the simple fact that ice floats. Follow Worth Knowing for more things worth knowing.